Okay, let's get started. So just a reminder, next week is going to be your first quiz. You can look at sort of the layout of what it's going to entail. I was looking back through the book and the syllabus, and I just want to sort of make one clarifying statement in advance. So don't tell. I don't want to hear things. It doesn't seem like everybody's here recording this, relay this to people, but this is generally the way that I operate. Is I'm trying on the syllabus to provide guidelines for how to and what to expect on the quiz. You have to give me a little bit of wiggle room on that. In general, when you've had a quiz, or usually my thought process is when you've had a weekend, as I think I said last week, when you've had a week to prepare, if I've presented the material and you've had a weekend to prepare for it, then I figure it's fair game. An example of where that's going to come up, perhaps on the upcoming quiz, actually certainly on the upcoming quiz, is that there's an alcohol chapter in the book. And I may not necessarily teach in the order of how the book is. And a perfect example that I was looking through the book and I was like, oh, wow, I overlooked that. But it's just how I'm sort of operating. It's that the Williamson ether synthesis, right, which we went over, is technically in the ether chapter, right? That is a fair game reaction because I presented it. So the way that the book presents everything is not necessarily exactly how I'm going to present it. So it's just important that the spirits of having you responsible for alcohols is more what I want you guys to sort of keep in mind. So if I presented it yesterday, or if I present it today, it is fair game for next week. In addition, and towards the end of last class, many people had sort of come up to me and asked me a little bit about Organic 1. Obviously, Organic 1 material is going to be very, very, very important, and there will be specific quiz questions on this upcoming quiz that are going to be based upon the reactions that you need to know for Organic Chemistry 1. Now, the easy solution that I can tell you is all my Organic 1 material is on the website, so you can go back and check that. I recognize that may be a grandiose effort to actually have to go and revisit an entire coursework of material. Perhaps a more defined way in which you can do it and figure out what reactions specifically that you're responsible for is that in the back of these chapters, there's actually a summary, right? In the back of these chapters, let me get to them, right? At least in this one it becomes green, but at the end of each chapter there's usually a summary, that's not it, there's a summary usually of the different reactions, okay? And so that's maybe one abbreviated way in which case you can go about them. But again, what you're responsible for is the Organic 1 chemistry that we learned, so substitution, elimination, chemistry of alkenes, right? And chemistry of alkynes, as well as some little work. Again, really all that we learned for organometallic chemistry was the synthesis of Grignards and the synthesis of cuprates, and the sort of idea that things like Gilman's can do chemistry that SN substitution chemistry can't.
Do you have to know like the specific mechanism?
Yes, 100%. Yes, yeah. I think that the mechanisms. So this is worth stating as well. In general, and so I would say that this is true for your knowledge of the Organic 1 material in terms of the mechanisms. I got to choose my words carefully here because this can be interpreted in different ways. Usually when I go through mechanisms, I'm trying to go through mechanisms in a way in which case you are building upon past mechanisms. Right, so you're sort of you're not sort of seeing the chemistry for the first time. Throughout the course of the semester, you come across some that don't necessarily fit with that trend and that are a little bit more challenging. So I think to give you an example of a mechanism that I'm not going to ask you this upcoming semester, or from Organic 1 that's not going to come up in this quiz, an example of that would be osmolysis. right? Ozonolysis is a little bit more of a challenging mechanism that certainly I would encourage you guys to learn, but I realize that especially since people are trying to catch up on all these mechanisms, that may not be a mechanism whereby you can build off of that. Reactions such as hydration of an alkene, right? Acid and water, addition across an alkene, bromination, right, of a system. These are reactions that are much more up the avenue. So I can't give a straight answer, but maybe that gives you guys a little bit of feel. Transition metal catalyzed processes, we really have not spent any time on mechanisms of transition metal processes. We'll spend a little bit of time later on in the semester when we get into cross-coupling and metathesis chemistry. The only real transition metal type of chemistry that we discussed last semester was, for example, hydrogenation of alkenes, right? And so again, the hydrogenation of alkenes is not really your typical mechanism where you're going to draw typical heterolytic bond-forming reactions. So certainly I would encourage you to study some of the more basic radical mechanisms, in part because we'll see that a little bit, but really in terms of prioritizing, what I need to make sure everybody's up to speed on is being comfortable with those sort of typical sort of heterolytic, mechanisms. Does that make sense? Okay. All right. And I'll try to, as we're going through the material throughout the semester, I'll try to sort of put into perspective in the new reactions that we learn, those that I think, you'll be more responsible for knowing the mechanism for, and those that you won't be. So, okay. Any other questions? Yeah.
Do you make the quizzes or do you trust the station?
I make them all. They're made. Quizzes are done. I have to double check them to make sure there's no mistakes, but I wrote them. So, and I think I said there's going to be 4 questions on reactions, like name the start. This you're writing this down. You can find it in the syllabus, right? I explicitly said this on the syllabus. There'll be 4 questions that are testing your ability to remember reactions, and so you'll get some questions that may ask you, here's the starting material, here's the reagent, what's the product? You'll get some questions that will say, here's the starting material, here's the product, what's the reagent, right? And something that I've only been doing in the last year or so, but I think is worthwhile, is I'll give you the product and the reagent, and I'll try to get you guys. So there's one of those on each of the quizzes. There will be one question like that. And no, you can't just give me the product as the starting material. That's not a trick that I'll go for. So again, that's to try to help think a little bit more backwards, which actually benefits when we start getting to synthesis. And I do think that it helps a lot. It's just that students need to be encouraged to think in that way a little bit, and I feel that those types of questions do seem to be paying off. So that's going to be 10 points, 2.5 points for each. And then you'll get 2 questions on mechanisms. One of the mechanisms will be one from last semester, and one of them will be from this semester. Okay? And I'm not sure that I was necessarily 50-50 on question 1. I can't remember, but I tried to mix it up. So. All right. Okay. All right. Any additional questions? So those are going to be at your recitation sections. I guess I'll say in advance, and this is going for exams as well. This is organic chemistry. Cheating is not tolerated. And so within that, I try to do things that will hopefully prevent as much as possible. One of those, which is obviously students leaving midway through exams. So there's a hard rule that once you look at your quiz or once you look at your exam, you stay till you're done. In fact, with the quizzes, you stay till the time period is over. Because if somebody's coming in late, for example, it's just to avoid those scenarios even happening. I don't even want any sniffs of potential in that regard. So, okay, so just show up on time, but also don't show up, if you think you're going to have to go to the bathroom. Take care of that before you show up. So. All right, so last class we left off talking about chlorination and bromination. And I mentioned how particularly it comes up with chlorination, right? If you have a system where you have some chirality on this molecule, and generally when we're talking about chirality, we're really speaking exclusively to secondary carbons now for reasons that will hopefully be clear, right? When you have secondary alcohols that are chiral, right? When you do chlorination, right? Chlorination is generally carried out with a base, okay? And as it turns out, and I'm not going to go into depth on this, but just in case some of you read this, it turns out that the choice of base can actually have an impact on whether you get inversion or retention. I focus, and I don't even teach the inversion. I don't teach the retention, I only stick with inversion because it makes sense. Usually it's a tertiary amine that does that, but I'll just simplify it even further and say base. If in a synthesis problem, for whatever reason, you want to invoke inversion, if you want to invoke retention with pyridine, you can, I guess, do that if you want, but you've got a lot more stuff to learn, so let's just focus on what I'm teaching, yeah.
Pyridine retains,
Inverts.
inverts at pyridine.
So, retains. But I'm not teaching it. And now you're going to be confused. So I'm going to keep it this simple as I want. So there's this weird, don't worry, we've got a lot to cover today. Forget I said anything. Thionyl chlorination with a base inverts stereochemistry, and we'll leave it at that. Okay, so if you have a chiral alcohol, and you treat it with a base, you will get the inversion of the stereochemistry of that chloride. So whichever direction the oxygen is going, you will get the inversion stereochemistry. So the chlorine will come in from the opposite phase. And again, we can invoke this, right, based upon the idea that once you're sort of at that intermediate, right, wherein we are, so this would be if the alcohol's up. Right, so if we're at a situation like this, right, when the chloride ion is going to come from the backside attack, right, depending on how you want to draw it, I'll just probably go all the way up to there, right, you will eventually get your inversion. So we can rationalize the inversion of thionyl chloride with the understanding that it's an SN2 reaction generally, right? And so for reasons that are obvious, if it's a primary chloride, stereochemistry is irrelevant, right? Because it's not going to be chiral, it's a primary alcohol. If it's tertiary alcohol, why is that irrelevant? Because there's no possibility for SN2 because it's going to have to go through SN1. So if you try to do this chemistry on a tertiary alcohol, you'll racemize or you'll start to potentially do other stuff. So, but at least from the stereochemical purpose, it's that. So when we think about halogens, and the same thing will carry with the bromination as well. Same thing with PBr3. If you do the PBr3, you'll get that inversion as well. Okay, so these sort of mechanisms that we invoked that are sort of have this SN2 reaction in them will lead to inversion. Now, if we think about where we've primarily viewed halogens, we find them valuable reagents, right, in large part because they are good leaving groups, right? And so they can basically serve an additional role now as electrophiles to potentially do additional SN2 chemistry. And so if we're trying to do stereoselective synthesis, right, and we want to install a leaving group, and we have an alcohol, and that's got some stereochemistry, we can chlorinate it, that's going to invert the stereochemistry, and then we can add a nucleophile and it'll go back to the original, right? So there's this ability to, when we're thinking about SN2, this sort of inversion and additional inversion, you guys can begin to keep track of what the outcome of the stereochemistry will be. Another, I think a little bit easier to see method for making sort of carbon-based electrophiles, in addition to halogens that would retain stereochemistry without having to go through this fancy, retention chlorination chemistry, is, I think, something that's much more rational to you guys, and it's the use of molecules basically called sulfonates. Okay, and so sulfonates and I'll just show sort of mesyl chloride. Okay, if you take this molecule and you treat it with triethylamine as well, okay, what's going to happen here, right, is that you're going to react chloride to and then with these tertiary amines that we're going to see quite a bit, like triethylamine, it's a very, very common amine base. Right, so you guys see that we're going to sort of take the electrons, we're going to make that bond, we're going to get up this intermediate here. The purpose of the triethylamine that we often see here is you could invoke this same mechanism with the chloride ion, deprotonating, but then you're generating HCl, and as you might imagine, HCl might be problematic. So when we think about these tertiary amines, right, now what you have is what we call a sulfonate. Okay? Question, yeah.
How is the alcohol group attacking the sulfur if, like, didn't we say that it has to be deprotonated in order to attack?
No, I never said it had to be.
Can attack on its own? Like
Yeah.
an alcohol group itself?
You saw it. Yeah, you saw that happen, right? We've seen that. There's two options, right? You can do it in a neutral form, in which case it becomes positively charged, or you can deprotonate it. So triethylamine is not quite strong enough to deprotonate an alcohol, right? The pK of triethylamine is like 12 or so. So you'd have to have a lot of triethylamine in order to deprotonate that. So, so generally when people invoke these mechanisms, it's the alcohol attacks first, and then the triethylamine will scavenge it. You could certainly imagine a mechanism in the opposite, but usually that's not how people draw it. Again, because the pK differences are too far away. But the important sort of point here, right, is that you now have, in this case, you have a leaving group with one stereochemistry, and now in this other case, you have now a sulfonate, right, which can also be a good leaving group. So, for example, if you took a nucleophile of some type, right, and attacked this molecule, right, you would now have your sort of nucleophile plus OS minus, right? And in the case of the chloride, right, this is kind of what I'm getting at, is within, say, for example, a synthesis problem when we're considering this. Now we're going to come from the opposite face, right? And so, again, whatever that nucleophile is, if it's an alkyne or something else, I'm just leaving it to be variable at that point. So the idea is that if you're starting with an alcohol and you want to convert that alcohol to something else, through the process of converting the alcohol to a leaving group followed by additional chemistry, right, you have some versatility here, right? If you go through the halogenation, following an additional SN2 reaction, you'll get one stereoisomer. But instead of going through the halogenation, you can go through this sort of, you can make the sulfonate, right? And sulfonates are actually pretty valuable. I've shown the methane sulfonyl chloride. There's a very, very electronically poor one that's called a triflate, which in fact you don't even use the triflyl chloride, you use the sort of anhydride of it, which you can find in your book. That's an even better nucleophile. And so based upon changing the nature of this group here, you can actually attenuate the electronics of that, so it's pretty versatile. But just to keep it sort of simple, we'll stick with the methane sulfonate just because it's smaller and easier to draw. Right? So is this clear? Does this make sense? So again, simple. You know, this is in essence, which I think that the point is being brought up. This bond that we're making is analogous to the Williamson ether synthesis, but we have, because of the nature of the reagents and the nature of the base, we have staggered the protonation event a little bit differently, right? But it's still, at the end of the day, it's the same net outcome, right, of making a bond between the oxygen and sulfate. All right, so we clear? Okay, so take-home lesson, there is stereochemistry involved in converting these alcohols to leaving groups. We've got a couple options here in which case to do that make them complementary to one another. Okay? I just sort of shown this, and I just popped it in my head, and so I'll say this as well. I'm showing it the importance of substitution here for that second stereochemistry step. Just sort of reflect on organic 1. Is there another? And I'm not gonna I'll leave this out there and have you guys think about it a little bit because I do want to get through all the reactions today. Maybe I'll come back if we have more time. But there's another potential stereochemical outcome of a reaction that we learned besides SN2, right? That where you can sort of get conserved stereochemistry, right? And that's elimination chemistry. And so sometimes the stereochemistry of the leaving group will have an impact on the stereochemistry of alkenes as well if you're trying to do elimination. So if we have time, we can talk about that, but you guys should be able to think that through, right? Because you need that anti-periplanar relationship, and so the stereochemistry becomes important, okay? So a lot of reasons why having a specific, a leaving group with specific stereochemistry could be valuable in synthesis, okay? All right. All right. All right, so last class, one of the other things we talked about that I think is worth repeating because I realized that it's in chapter 10, I sort of alluded to this last week, right, is that we had this discussion on reaction reversibility, right, and the classic, and one of the examples that we gave was like the acid-mediated esterification. And it turns out that if you did similar type of chemistry in an aqueous media, you could actually break the ethers and generate alcohols. But one of the reactions that we saw last semester that I actually alluded to yesterday as well as this morning in class, right, is if you take, say, for example, an alkene and some strong acid like sulfuric acid and water, right, what's the reagent and what's the reaction that we get? You get an OH. And yeah, so you add water across the double bond, right? So what happens, right, is that the electrons, right, will protonate, right? In this case, we don't have to worry about Markovnikov because it's symmetric. Right, so I'll just put it there. So the electrons in there will make a bond with the hydrogen. Will generate the sulfonate. Right? Very similar to what we saw when we protonated alcohols to do the dehydration to make ethers. Right? Then what's going to happen is that water's going to attack. Right? That's going to lead us to this molecule here. Just draw out the hydrogen bond because we're going to pluck that one of those hydrogen bonds off, right? And then again, as we sort of discussed the choice of what you want to deprotonate here, give you guys a little bit of flexibility of what to do here. If you want to use the bookkeeping method, you could use the sulfonate. I oftentimes like to do that just to sort of keep track of everything. But you need to, you could also use water, which is probably more likely what's happening. Because there's so much more of it.
You said water is more likely to happen?
Yeah, just there's more of it. It's usually, like in this case, it's a solution of water. There's more of it. The pKa's are fairly close between sulfuric acid and water, but in terms of the protonation event, but perhaps driven even more so by just the fact that usually these systems are loaded with water to sort of drive these reactions. What I said was it doesn't matter, if that helps make you feel a little bit better. For me, at least. But yeah, so this is a reaction that we learned last semester, right? It's one of the key and one of the very early reactions of alkenes that we learned. Abraham, yeah. It's irrelevant. It's irrelevant, yeah. It's not a chiral molecule. So, but with this type of reaction, you're going through a carbocation intermediate, so it could in principle attack from either face. If there was stereochemistry involved, which I don't have time to get into, because of the fact that it's going through a carbocation, because of what we're going to talk about, the fact that it's reversible, it'll probably be driven by thermodynamic stability. So if there happens to be other stereochemistry nearby, you may get reaction driven by thermodynamics. But yeah.
Sorry, can you explain what happened right there?
Right where? This last step? This last step? This is just, after we added the water in, we have H2O plus, right? The only bond that we've made here is between one of these lone pairs and that. The two hydrogens are still there. I just drawn them out, right? And what we need to do is we need to take off one of those protons to sort of neutralize the system afterwards. And this is why I was saying you have a couple options of what you can use to take off that proton. You can use the water, you can use the sulfonate. Like I said, I usually, since I have it in the equation, sometimes I like to just keep that because it helps me with my bookkeeping, but water is more likely to be what's doing it. But so what I said yesterday as well, right, and then I'll go through here, is that what drives this process is the water, right? So if we add water, it's going to go in that direction, right? So the Chatelier's principle, you put reagent on this side, you push it that direction. By contrast, right, if you remove water, right, from this side, right, you can drive it in the reverse direction. This is kind of what we were talking about last class about things like Dean-Stark apparati and molecular sieves and so forth. So basically, if we did this reaction in the reverse and lost water, right, it's going to be all the same intermediates, and we're basically just going to be doing everything in reverse, right? So at this step here, right, what was the last step? Deprotonation. So what's the first step? Protonation, right? Yeah, so first step is protonation. Right? So basically it's the reverse, right? So I can get rid of that, right? Now what's happening between here and here? The water was adding in to go from here to there. So what's the reverse? The water's leaving, right? So we're just going to change that arrow in reverse. And change our arrows here, right? And then what's the final step, right, in this reaction? Well, we basically took the electrons that were in this bond and made a new bond. So what's going to happen? The reverse of that is an elimination, right? We're basically adding electrons, right, into that bond. In this case, there's a protonation event. So we're doing a deprotonation along with dumping electrons and making that double bond. That's elimination, right? That's the elimination process. So in this case, I have the sulfonate here. Water's a little closer. So makes my life a little easier there, right? And so this is basically the mechanism of an elimination of an alcohol, which is another reaction that pops up in Chapter 10 that we also did cover last semester in my class, but I thought it was worth sort of mentioning this reaction as well. In general, the reagent that people generally refer to in this, sulfuric acid, will work. Usually the textbook reagent is phosphoric acid. Doesn't really matter to me, but I'll just know that it's strong acids can do this. Yeah? Claire, you usually sit up front. Is it cooler back there? Okay.
When we're taking it back, are there any other conditions that change that have it to go in the reverse direction?
Besides the water? Yeah, that's a broad question. I mean, could there be thermodynamic control, for example, leading it one direction or another? Sure. Well, so there's lots of things that can influence what direction a reaction is going to go with, right? And so I could spend the rest of the class going into depth about what that is. I'm choosing to focus explicitly on Le Chatelier's principle and the point that within dehydration or hydration reactions, which come up in a few different reactions that we'll see, and just sort of show that by leaving water, by trying to get water out of the reaction or by adding water to the reaction, you can actually influence what the outcome is. Based upon shifting the equilibrium in that capacity, but other factors certainly can can drive these reactions. If it happens to be on an alkene that's highly strained, for example, that doesn't want to exist as an alkene, right, then it's probably going to favor the alcohol, right? If for whatever reason it's the opposite, like we'll learn about aromaticity later on in this class, right? If by eliminating water, for example, and going in that direction, you make a benzene ring, well, that's going to favor the elimination reaction. So certainly thermodynamics can also influence this. But for now, we're just focusing on sort of Le Chatelier's principle. Does that answer your question? Okay. All right, so okay, so that's some of the more, I think, basic alcohol reactions, and so we're going to spend a little bit of time getting to a few maybe fancier reactions. So since we're on dehydration, maybe now's a good time to discuss. Sort of revisit carbon alkyl migrations. So anybody who had me last semester knows that my take on carbon skeleton rearrangements, right, is one where you guys should know how to do them. I will rarely ask you to predict a product that invokes a carbon skeleton rearrangement. If you get a question that has a product that involves that skeleton rearrangement, at that point, that's kind of in the context in which case you guys need to understand sort of carbocation rearrangements, right? So usually those questions will come to you from the standpoint of, here's the product, it went through a carbocation rearrangement. You should certainly be able to show a mechanism that can invoke that. There's a couple exceptions to that rule, and one of them is a pinnacle rearrangement. Okay, which is a dehydration reaction. Okay. So this molecule here is pinnacle. It's when you have a 1,2-diol. So it's an organic 1 refresher. How do we make diols?
That's all that.
Huh?
That's all that, right?
Yeah, the first lab.
Yeah, this is lab. This is lab 2.
Oh,
Yeah.
great. Timing it well. How do we make the diols, though?
Yeah.
Yeah, so from an alkene, right? So we take an alkene. The quick way to do it is osmium tetroxide. So OSO4. Sure, I didn't teach that though. Probably. Yeah, it's fine. Sure, use it. So another method that we may have discussed, but we'll certainly discuss next class, will be another way that we can make diols, which is from epoxides. Hydrolysis of epoxides, which we'll discuss next class. But from alkenes, osmium tetroxide is the go-to way, right? Okay, so we know how to make that if we had an alkene, right? And it turns out that if you treat this molecule with sulfuric acid, you can actually get a carbon rearrangement. And so this is going to be fair game for the quiz, okay? So it's a good opportunity to revisit alkyl migrations and sort of 1-2 shifts. So these are carbocation rearrangements. And so the first step of these reactions is the formation of carbocations, right? And so in this mechanism, the first thing that we want to do is generate that carbocation, right? So it should be pretty easy to do. We've been doing this kind of thing quite a bit the last couple days, right? So how do we do it? Yeah, somebody that hasn't talked a lot. Yeah.
You can protonate on one of the alcohol,
Mm-hmm.
and then leave, and then.
Hold on, wait, you're going too fast. Okay, so we're going to protonate. Let's break it down, right? If you guys are quick to mentally jump around. Take the time to draw out your intermediates and work on this stuff. Okay, what am I missing here? Charge, correct. Okay, now what?
Then that's gonna leave.
Okay, how's it going to leave? Where are the electrons that are going to make it leave?
The ones that are attached to the carbon.
So yeah, the ones that are attached to the carbon. So it's going to leave, so it's going to leave through a mechanism whereby the electrons that are on the oxygen carbon are going to go away. Right? That's going to generate water. Right? Right? And then what we're going to have, right, is the carbocation that was mentioned over here. Okay? Now I'm going to draw this a little bit before we keep going with the mechanism. I want to draw this and use this as an opportunity to revisit another Organic 1 concept, which is hybridization. Okay? When we deal with hybridization, right, as you guys by this point all know, right, you spent a month talking about tetrahedral geometries and so forth, but when we're at a cation, what's the geometry of a cation? And what's the hybridization of a cation? Yeah, it's sp2, right? And what does that mean in terms of the geometry? Right, that means it has an empty p orbital, which makes the geometry planar, trigonal planar, right? And so oftentimes I like to sort of, I find that oftentimes when I draw carbocations, you guys that had me in the past know that I'll often like to, I think when we're sort of drawing these mechanisms, sometimes it's helpful to actually show that empty p orbital, show it, right, in an empty p orbital. In this capacity, right, we can sort of now imagine a scenario where the electrons that are down here, right, if I want to draw this with the appropriate stereochemistry, it doesn't matter, so it's not a stereospecific process either way, but I'm just trying to draw it for completeness here. What's going to happen, right, is that the electrons down here, right, are going to end up basically doing a 1-2 shift. So again, I feel like I'm saying this over and over again. Jose, you had me. So when we talk about stabilization, right, this is oftentimes a nice way to reinforce some of the previous concepts we learned, right? As I have those electrons lined up to that empty p orbital, it's going to do a 1-2 shift. But what also is that arrangement indicative of? Stability, right? And what's that stability? What's that stabilizing? Give me a little bit more.
Well, a tertiary carbocation is more stable.
And what is the principle that makes it more stable? That I've tried to draw very suggestively there. Nothing? Yeah.
I could be wrong, but hyperconjugation.
Absolutely, hyperconjugation, right? So hyperconjugation is what drives stability of, right, that tertiary carbocation, right? Hyperconjugation, conjugation would be if it's electrons, you could actually draw resonance form, right? Hyperconjugation is something in between, right? It's the fact that there are still electrons here, right? And in many ways, those electrons, as they begin to line around that p orbital, they get pulled in that direction a little bit. And the more of that you have, right, the more stabilization electronically of that. There could be steric arguments as well, but yeah.
But the reason that this is happening is not because hyperconjugation is causing it to happen, but it's going from a tertiary
Right.
to
I'm revisiting hyperconjugation just to remind everybody. Because I think that when we're talking about alkyl migrations, when I think of alkyl migrations, I think of them as being a fantastic opportunity to revisit the concept of hyperconjugation, because it's almost evidence of hyperconjugation in many ways, right? Because these electrons are being pulled over in this direction, they're being pulled over, it helps stabilize that, and then they cross that energy barrier, and they end up right, and you basically end up with, take advantage of my multicolored that blue is horrible. Didn't blue, it's like aqua. All right, sorry, I won't do colors here. But yeah, so these electrons. All right, so this guy's going to pop over there, and it's going to become that molecule over there, right? And the inverse will happen as well, right? The inverse will happen as well. These could then, you can imagine, stabilize. So certainly, as we've talked about the other chemistry, the potential for something like this to happen is reversible, right? But certainly something forces it and drives it in this direction. Of those options, which is more stable, and at the end of the day, it probably isn't even this. It's the final product that's ultimately formed. But there is another, I think, point to perhaps dive into in terms of this being more stable. Somebody that hasn't. Okay, yeah.
I'm not sure if this is right, but I also have a question. Is it that once it hits a certain point, that oxygen electrons just kind of
Yeah.
move
So
in
well, right. So this is what this is called. What? Hyperconjugation. Those lone pairs. What's that? Yeah. Inductive effect is a little bit more of a broad term. That's, I just said, this is hyperconjugation. What's that? I'm restating the word hyperconjugation to make a broader point here. That's conjugation, right? So conjugation, you guys are saying all the right things. I'm hearing all the right terms. Resonance forms, right? Resonance forms, the fact that you can draw a resonance form is further evidence, right, that you have full-blown conjugation, right? Those electrons are actually conjugated, right, with that system, right? And we'll talk a little bit more about conjugation within double bonds, for example. That'll become more clear, but this is just as well, right? And so the resonance form here that we can imagine is this, which is probably a more stable resonance form anyway. Why? Rachel? No, this is not an enol. Something else. Danny? Yeah, exactly. So you've got your octet filled here, right? Here you don't. So filling the octet rule is a valuable driving force. This is a perfect example of the value of that, because if it was based upon electronics, for example, the oxygen is more electronegative. So in general, an oxygen you might not want to think it's going to take on a positive charge, but because of the fact that you have a full octet, this is better. And then then simply deprotonate that. Right. Right. Okay. So this is something you guys. This is a good opportunity. The Pinnacle is a good opportunity to revisit alkyl migrations. If you look in the book will occasionally have Pinnacle mechanisms that might be a little bit more complicated in ring systems and so forth. Yeah.
So I know that is the right answer, but in this case it's kind of reversed, like the way that the mechanism occurred, the ketones on the other carbon and the 3 methyl groups.
Oh, yeah.
I mean, it's the same thing, but it's just a little confusing.
Yeah. It's the same object, yes.
Yeah.
But just to make it a little bit more easy to see. Okay? All right. So how are we doing with time? Okay, perfect. All right. So so another group of reactions that I want to talk about, and maybe I'll introduce this. I'm kind of going off the cuff here with this, but the So when you guys hear the term, I wonder if this is going to complicate this more than it should be. Whatever, this isn't that. I think this is kind of interesting. If it works for you and makes sense, great. If not, don't worry about it. But when we hear the terms oxidation and reductions, right, what do we normally think of when we hear these terms oxidation and reduction in terms of classic general chemistry terms.
One is losing and one is gaining.
One electrons, right? So do you remember which one is which?
And going back to general chem, yeah, oxidation is losing and
Yeah.
reduction is gaining.
So yeah, and words that you use imply something. The oil rig, right? That people often use is the sort of term to remember. So it's oxidation is loss of electrons, reduction is gain of electrons. And so in organic chemistry, we're going to be talking about oxidations and reductions, particularly of carbonyls. So we've heard reduction in the past, right? With where have we heard the term reduction in organic one? Yeah.
Alkene reduced
Yeah.
H2 and PD.
Right, exactly. So where you guys have heard the term reduction in the past, right, is that basically, you know, if you take hydrogen and palladium, right, we're kind of reducing the sort of the double bond, right? And so in essence, what's going to happen is we're going to sort of reduce this, right? And through the process, this molecule has overall, you can sort of maybe draw a parallel here because it's a reduction. It's a gain of electrons, so overall the molecule has effectively gained, it's gained a couple protons, it's also gained a few electrons. So from that standpoint, you can maybe sort of see how that term might, that maybe is a little bit easier to see when we're talking about maybe a transition metal losing an electron versus an actual organic molecule losing it, right? So that's why you might call that a reduction. So when we talk about alcohol, we're going to start to get into alcohol oxidation chemistry. And when we talk about alcohol oxidation chemistry, it may be a little bit more confusing, and so it's perhaps worth sort of taking a look at the sort of terminology that we have here. I think on the first standpoint, it's maybe a bit easy when we're thinking about going from an alcohol, right, to an aldehyde, right? So this is a molecule we're going to be focusing on in a bit called aldehydes, but we'll talk about how to make them. Right now, one of the next chapters are going to talk about the versatility of those in synthesis. But if we were to do this process, this would be an oxidation, right? And the term oxidation here, in a way, what we're doing is the reverse of this, right? It's sort of like, in a way, right? Let me just do this, right? It's kind of, right? I've just kind of drawn over the top there, right? We've kind of just lost an equivalent of hydrogen. And so when we talk about oxidations of carbonyls, in many ways it's kind of the inverse, and we can think about it from the standpoint of the hydrogen, right? So we're going to oxidize, and we're going to lose, right, an equivalent of hydrogen, right? And so this is one oxidation state, and that makes sense, right? There's a higher oxidation state from the aldehyde, right? That is a carboxylic acid. And this is maybe the one that's a little bit more tricky to see, right? So how is if we keep oxidizing, this is also considered an oxidation. But in this one, we've actually gained oxygen, right? So again, this is just kind of probably not the most important thing. Yeah, from the aldehyde.
Use oxidizing.
No, that's not what I'm asking. I'm asking about why is this called an oxidation, right? Yeah.
because the state of the carbon, it increases,
You're getting
it
oxygen.
becomes more positive.
It sounds like that, right? But it's not, right? It's not. Rachel, what do you think?
Could it be the electron pull of the oxygen pulls the electron from the way
No, not quite. I'm not going to let this linger for too long because I'm kind of asking you guys to read my mind here and see if anybody can see. I'll give 2 more shots. Yeah.
Isn't it that carbon gets an extra bond to oxygen? So like if you
No, it has nothing to do with the oxygen. That's the irony of this. Everybody thinks the oxidation. They hear the ox. They think of oxygen. No, the term oxidation is still coming from a loss. There is a loss of hydrogen here. Where's that loss of hydrogen coming from? Yeah.
the carbon. Yeah.
No.
Well, the aldehyde is,
No. No. There's something that's not being drawn. Yeah, Christine.
Is that anything to do with water?
Yes. 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 Right? If we want to balance that equation, we need water in there. Okay. So in essence, to be able to go here, where's that oxygen coming from? Well, the oxygen is coming from water. So what's the overall process? Well, the overall process is also eventually going to leave that equivalent of water. So again, this is not that important, but I think it's sort of just an interesting realization of how the terms, come into play. Because I do think that it's a common misnomer oftentimes that the term oxidation somehow has to do with oxygen, when it doesn't. It's got its same roots as sort of oil rig that we discussed in the past. So losing the electrons from that water, this is an oxidation, right? Because really the overall process, it's not complete, right? We need to consider the water in that equation as well. Okay, so it's an overall oxidative process. Okay, Henry, yeah.
The water is being oxidized and the aldehyde is being reduced.
No, it's okay. I think when we go through the mechanism of this, it's the oxygen, the water is also losing.
Yes.
Actually, the water is neutral. The water is going from having two bonds, right? So the water is going from having two bonds. So the water is basically. Now you got me all confused. But it's.
This is even
Just say, wow, it's so, wow, I didn't know that. Okay, so all right, so anyway, all right, so there's a couple ways that we can do oxidation chemistry. I generally haven't taught, so I'll show the ones that, whatever, I'll show them all. So I'm going to start with, hopefully I'll have enough time, I'm going to show you guys a couple of different ways. These are transition metal catalyzed processes, or not catalyzed, actually, not catalyzed, sorry. It's chromium mediated. It's actually reagent based. So the chromium throughout the process is actually going to, as it oxidizes, you'll see the chromium is what ends up getting reduced. So the classic chromium reagent that we generally consider here is something called Jones reagent. Okay, so Jones reagent is what you basically do is Jones reagent is a mixture of CrO3, right? So that's, right? So if you take chromium, right, and you mix it with sulfuric acid, right, and the sulfuric acid is generally in water, what you get to is, in essence, the active, what we oftentimes consider basically chromic acid, which is this molecule here, okay? Now, last semester I'm not sure we talked too much about this, but I'm just going to sort of talk about oxidation states of metals very briefly. We'll come back to this a little bit later on. But when we talk about oxidation states of metals, we'll often refer to the oxidation state at the chromium based upon, in essence, how many sigma bonds it has. So, again, without getting into too much, for the most part, when we see these, we're not going to be referring to dative ligands. I'll maybe just try to stick with the covalent type bonds. But you'll notice it has 6 bonds around it, okay? And so oftentimes, it's got 2 double bonds and 2 single bonds, so in total 6. So 1, 2, 3, 4, 5, 6. So 6 bonds total. And so we're going to give this an oxidation state of 6. The same oxidation state as CrO3, okay? And what's going to happen here, right, is when this oxygen reacts, right, when this ends up reacting with chromic acid, right, what's going to happen is we're going to invoke a mechanism, and I'm going to try to simplify it a little bit here, just to make life easy. I'm going to show it in the protonated state. I'm just trying to get through this. I just want to get to the intermediate. In reality, that hydrogen would probably need to be on the carbonyl, right? Just because of resonance stabilization. But the point is here I want to get to the important intermediate, right? And following loss of, water, eventually. Effectively, we're doing kind of the same thing we did with the esterification, right? So instead of making a bond between the oxygen and another carbon, right, we're now making this sort of chromate ester here. So the oxygen is making a bond with the chromium. Notice that it has the same number, that's just a substitution type reaction, right? It's going to have the same amounts of electrons in it. Now, the mechanism from here is a little bit more complex, but what I can tell you, and what I want to show you guys, right, is that if we invoke, and we were talking about this in recitation yesterday, right? We've seen a lot of chemistry with, right, where you have a leaving group, right, around a carbon, right, and how you've got the carbon-carbon leaving group with the beta hydrogen. Really, if we substitute, if we think about this molecule here and we think about this molecule here, right, if that was an oxygen, right, and if that bromide were this sort of chromate region here, which is at a high oxidation state, that chromate also kind of wants electrons, right? It's sort of an oxidation reduction type mechanism. But if we invoke a mechanism where, say, for example, water is able to do an elimination, right, we're going to get to our aldehyde, right? And in the process, notice that what happens to the chromium is the chromium, at least in that intermediate, you can have water added and so forth, but notice the chromium is now at 4. So what has happened to the chromium? What's the nature of the chromium? It's gone from 6 electrons to 4. All right, sorry, I'm misspeaking when I'm saying this. Can I take like 5 steps back? When I was talking about the chromium being 6, I kept saying electrons. I was misspeaking. The analogy to this being chromium 6 is as if these are deficient. So I completely misspoke. So I want to try to step back and reset that because I misspoke. Think about that as almost like a 6+, right? So it more refers to electrons not being in there. So when a metal is at a high oxidation state, it's got a high number, right? Because it's lost a lot of its electrons. The electrons are sort of being tied towards those other bonds. I'm sorry, I know I had to step way back. Are we clear on that? So just to try to put it as simply as possible, this number reflects how many electrons this metal is missing in a way, or is deficient in, right? It's not exactly that because it's a little bit more complex, but for the sake of this course, let's say that, right? And so by doing this, we're giving it electrons. So to go from 6, we've gone from 6 to 4, right? We've effectively given it more electrons. It doesn't have to share those in those bonds, right? So this overall process of giving it electrons, what is that? It's a reduction, right? So does it make sense now, right? So the chromium is being reduced. Meanwhile, the aldehyde, or the alcohol, is being oxidized. Clear? So the chromium is a high oxidation state, it's losing electrons, and through that process, right, you are oxidizing the alcohol. Okay, so a lot going on here, but this is the general mechanism of the first step, okay, of a Jones reagent. But here's the thing about Jones reagents. Is it quick?
Last one.
Okay, quick.
See the chromium, is it still considered 6?
This one is 4.
Oh, that's 4.
This is 4. Yeah, so that's why I was saying it goes from 6 to 4.
So the Roman numerals has
So that's an I before the V. Yeah. So it's still Roman numeral, but now it's it's now 4. Oxidation state 4. Okay. Now here's the thing about Jones reagent. Jones reagent does not stop at the aldehyde. Aldehydes rapidly oxidize to the carboxylic acids as well. So you don't stop here. I know I've got a lot going on here. I'm going to just to make some space here. Right? And the question becomes mechanistically how? Okay? Now the mechanism to sort of do this, and we'll get into how much time do we have? Because I do want to get to 10:30, so we've got some time. Okay, so I think I've got the perfect amount of time to finish up what I want to do. Okay, so the key here is that in a Jones reagent, one of the keys to Jones reagent, which is going to separate it from a reagent called PCC, which we'll discuss in a moment, is that the Jones reagent is an aqueous reaction. Okay, there's water, right, that we talked about here. So Jones reagent is an aqueous solution of chromic acid, effectively. Okay? And when you have an aldehyde, okay, when you have an aldehyde, okay, and you have an aldehyde and it's in an environment of acid and water. I'm not going to go into this in too much depth. It'll become clear, so you're not really responsible for this mechanism for the upcoming quiz, but potentially for the exam, so I'm just going to sort of not go through this in detail quite yet. But when you take this molecule and you have, actually it's reversible, but it's much more reversible generally in the one way. For the vast majority of our groups, we'll show a few others. What you end up having happen here is, actually let me do this, H plus H2O. You get a reagent called a sort of a hydrate, right? So this is a hydrate where in essence you can, again, we'll get to the mechanism a little bit more in detail when we get to the carbonyls, but basically the water, this gets protonated and the water attacks that sort of beta carbon. So I'm not going to go too much into the mechanism here. But this reaction is under acidic aqueous conditions. So what's going to happen is when you have this aldehyde, you're going to begin to get a little bit, not a lot, but enough, right, to begin to get this hydrate. Okay? And when you have that hydrate can eventually form the analogous chromate. So basically the analogous chemistry that we just showed. Right? And now when we do that same analogy to what we did over here, we do that elimination. We get to our carboxylic acid. Okay? So the ability to make this hydrate effectively brings in the extra water that we need to do that sort of final oxidation sequence. Yeah.
How is OH leaving in an acidic?
So okay, I'm shorthanding a little bit here. Realistically speaking, it's a little bit more complex than this, right? Proton up here is probably getting protonated, and the electrons are probably going up to that chromium. That's kind of what I was trying to get at earlier. But we got a lot to cover right now, so I'm taking a few shortcuts.
What do you mean by the proton from where?
So from the acid, I mean, okay,
So
okay, hold on. Okay, so yes, and let me just do it. I'm looking at the time, and I'm trying not to get too much away from this. But okay, so maybe I should have done this. Maybe I should have just gone right to here. Is that better? Same oxidation state. Okay, so do that instead. Probably better. Probably more. So you're not wrong. You're actually correct in your answer. So why don't we just
Okay, so you're saying
adapt?
chromium leaves
Let's just do this just to make it more. Let's just use that instead, because at least that way you're not. It's the same level of simplicity without complicating the mechanism, and realistically, it's a dynamic between these systems, anyways, in an aqueous environment. So all right, a lot going on up here. But so this is I think the point that I'm trying to make here, the big picture here, right? And we'll talk about Sworn in a minute, which actually is the same kind of concept, is that we can, at least from the standpoint of trying to understand this reaction, we can kind of treat it in many ways like an elimination process, right? The electrons are being dumped in to a metal and changing the oxidation state of that metal, but in many ways there's an analogy to this oxidation, right? That's kind of what I'm trying to take this back to, is the elimination. In many ways it's analogous to that. In addition, so we got about 10 minutes. In addition, the aldehyde, if you never made the hydrate, you could never make the carboxylic acid. Okay? And that's PCC. Okay? So if you want to take an alcohol to a carboxylic acid, you use Jones reagent. PCC is effectively the same thing, but the P stands for pyridine. You guys know what pyridine is? So pyridine is kind of like benzene, but it's got a nitrogen at one of the bonds, right? And what that happens, and I have it written down, you can look in the book, but basically the pyridine actually makes bonds with this chromate. And so it deprotonates, excuse me. Take that back. So the pyridine will deprotonate this intermediate. And that salt, pyridine is kind of greasy, and what that allows you to do is now that pyridine chromate salt that does this same chemistry is soluble in organic solvents. The grease from the pyridine allows it to be soluble in organic solvents, right? Thus, you can actually run a PCC reaction under dry conditions. In fact, it's not only dry, oftentimes you run it under like molecular sieves as we were talking about earlier. Generally when people run a PCC oxidation, you're running it in a solvent called dichloromethane. Have you guys used dichloromethane? Right? Usually it's running dichloromethane, and you'll have some molecular sieves in the reaction to make sure that no water can get in there. If you do have water in there, guess what happens? You start getting some carboxylic acid side products. So it's really important in the PCC. That's the whole idea here, and that's the point that I want to take home here, is that they're both the same mechanism, they're both effectively the same reagent. The difference is water. Okay? Why? This hydrate, which we'll get to at the beginning of the carbonyl chapter how that forms, but for now just realize that it does, right? And that drives it. Okay? All right, I want to show you guys.
So we don't need to know the same mechanism.
Know the reagent. Know the reagent at this point. Know what Jones reagent is. Know what PCC is. Know what they do. Now, a quick question. One more quick question. I did this with a primary alcohol. To illustrate the differences between PCC and Jones. What do you think happens with a secondary alcohol? You get a ketone. With which one? Both. Right? Once you get to that, if that was now a carbon, right, you're not going to be able to do that same elimination, right? So the difference in PCC and Jones only really matters with primary alcohols, right? If you have a secondary alcohol, right, they're both going to stop at the ketone. Does that make sense? Okay. Yeah.
So this step then, is it reversible? Because you draw two arrows in the same direction.
Where did I draw two arrows in the same direction?
Uh,
Oh, this?
No, next step.
This?
No, right below. Right after the dial.
When my hand starts getting closer, you tell me to stop.
I
need to bring a laser.
So this step, you draw it with the same direction, like two arrows.
Oh, multiple steps.
Oh.
So I'm just saying, yeah, anytime I draw two arrows, doesn't mean reversible, because then one arrow would go in the reverse. So when I draw two arrows, I mean it's more complicated that can be illustrated in a single transformation.
Wait, are we required to know how exactly, like, the details of how to get to that, the two relations?
Well, not for this quiz, but for the exam, yes. We're going to go over this. This is going to be one of the very first reactions that we discuss for carbonyl chemistry. Okay, so it's not, you don't have to know this. What you need to know about PCC and Jones, because I got to get on to another reaction. The only thing that you need to know about Jones, right, you could get a question on the quiz that will say, here's an alcohol, here's Jones, or here's an alcohol PCC, what's the product? You could get a reaction where you're given an alcohol and either a carboxylic acid or an aldehyde, and you're asked to show what the reagent is. Or, conversely, you can be given the product and Jones, whatever, and you have to show a reasonable starting material.
So we don't have to know the mechanism.
Not right now. Not right now. Not right now. Because you guys haven't learned this yet, so I'm not going to... We'll learn this later on. So not now, but for the exam, yes.
We are going to get those questions in the quiz, the ones that you just said.
Yeah. So know them, know what the chemistry does. Certainly, hopefully this makes sense, but don't worry about anything else. Let me show you guys, because we're almost out of time for today. Let me just show you guys one additional oxidation reaction, okay? Which sometimes I teach, sometimes I don't, but I'm going to teach it. and I think I showed my recitation of this reaction. So another way, if you want to go to the aldehyde, another reaction that you can run is a Swern oxidation. Okay, so a Swern oxidation is basically DMSO, which is a common solvent, right? It's triethylamine, which is that HCl scavenging base we described previously, and some chlorination agent. Generally, people use oxalyl chloride. I'm going to substitute in thionyl chloride because that's what we've used. So it's a chlorination agent. I'm going to substitute in what's generally not used, but just to stay consistent with what we did previously, I'll throw in thionyl chloride, okay, for this reaction as the chlorination agent. Okay, this is another oxidation reaction. What's cool about this reaction is it doesn't involve toxic chromium. So this is one of the problems with chromium, is that you're using it stoichiometrically, it's toxic. You have this, it's just very, very wasteful, so it's not the most green of reactions. This one's a little bit more green, but a little bit more smelly, because you generate dimethyl sulfide, okay? So DMS, remember when you talked about ozonolysis, reaction you should know for the quiz? Ozonolysis, alkenes, right? For ozonolysis, the reducing group in there, right, was dimethyl sulfide oftentimes, is the case. So you reduce DMS to DMSO, so that gets oxidized when it's working up the reaction. In this case, we're taking DMSO and we're actually reducing it to DMS. Quick little story about this. There was I don't know if it was a true story, but I did my PhD at Boston College, and the chemistry department was right next to the football stadium. Do you guys know where DMS? I guess I should start the story with this. You guys know where DMS, where you may come across DMS quite frequently? At least the smell of DMS?
Eggs?
Sulfides are in eggs, so it's a similar type of smell, but in gasoline, so it's pungent. So this is often, so gasoline doesn't have a scent, but DMS is often put into gasoline, right, so that you smell it. So if there's a gas leak, you can smell the gasoline, because otherwise you wouldn't notice that you have a gas leak. Does that make sense?
Methane. You mean in methane?
What's that?
In methane. You mean it's added to methane? Natural gas?
Well, both. In gasoline, everything, right? So it's added to natural gas, it's added to gasoline.
Oh, yeah.
Right? Because they don't have smells to them, right? So in either case, if there's a leak, you would smell it, right? So somebody ran a Swern reaction. This is a story. I don't know how true this is, but this is at least, it might be an urban legend. But apparently somebody ran this reaction in the chemistry department at Boston College, and they dumped the aqueous waste down the drain. Maybe that's what happened. Or maybe they just ran it, and it went through the fume hood. Either way, this started going out of the smokestack area where the ventilation is coming out of. Very close to the football field. It was a football Saturday. This began to drift over the stadium. And from the story that I heard, I don't know how true it is or not, but apparently they evacuated the stadium because they thought that it was a gas leak. Rightfully so. Right? So everybody thought there might have been a gas leak in the stadium. They evacuated. And so there's a I don't know if it's an urban legend or if it's true, but there's a story that when I was there, it was sort of like no Swern oxidations on football Saturdays. Do we have time to go through this? Okay, so really quickly, I'll be really quick, and you guys can try to come up with this on your own. I guess I don't have this mechanism on the quiz, but be prepared for it on the exam. So I won't go through the details of it. But step one is you make that. So the chlorination reagent. Right? So you can certainly draw that mechanism, right? Because this is going to be exactly analogous to our standard thionyl chloride chlorination of alcohol. So this is a reaction that's going to be analogous to chlorination, right? At that point, this becomes an electrophile, okay? This then reacts with your alcohol. To eventually get, after deprotonation, that intermediate there, right? And then the final step analogous to the chromium, but now we're actually dealing with something we're comfortable with, positive, negative charges. The sulfur has a positive charge on it, right? And thus, by virtue of an elimination, similar to what we saw before, but maybe something we're a little bit more comfortable with, you'll get to that. So I will tell you that this is a mechanism that I've sort of not gone through the details of individual steps. You should be able to push electron arrows throughout this process. It's in your book, I believe. But this, I think, because it doesn't involve transition metals, this is perhaps, from a mechanistic standpoint, one that's maybe a little bit more closely associated with the chemistry that you're used to. So you're certainly going to want to know this. Not maybe for the quiz, but certainly for the exam. Yeah. Hold on. Oh, sorry. I have a quick announcement.